For it's finding exact values using special angles. And so we're going to use the unit circle when doing this. And I'm going to start off by drawing the X and Y axis, which is represented by the red line. So we have here 0 degrees, 360 degrees, and then we have 90, 180 degrees, 270 degrees. So this is the angles that we have based on our unit circle. And I have it written right here. So use a unit circle for all the red angles. And we're familiar with that from the previous lessons, right? So the part that is new is that we're going to introduce some special triangles. By introducing special triangles, we're able to represent angles as exact values while the calculator won't be able to do it the same way. So what I mean is if you do cos 30 on the calculator, this is the value you're going to get, something along the lines of 0.8660. Meanwhile, you have cos 30 degrees. Its exact version is square root 3 over 2. So it's a lot better to not round. So it's better because there's no rounding error. And this is the exact version. Okay, and so when possible, we should be using the special triangles and providing the exact version, and we'll go from there. So first off, I'm going to start off with the 45 degrees. So I'm going to cut this so that that's 45 degrees, and I'm just going to go all the way around, making segments like so, and this would be 45 degrees because it's halfway between 0 to 90 degrees. Between 90 and 180 degrees, you have 135 degrees because I did 90 plus 45. The angle between 180 degrees and 270 degrees is 225 degrees. And between 270 and 360, we have 315 degrees. So these are all the angles that can be used using the related acute angle of 45 degrees.
So the next version that I might have is So the next version of a triangle that I'll have is a right angle triangle that consists of 30 degrees and 60 degrees. So today I'm recording outside, so you might hear random noises and bird noises, and I'll see how this goes. So the first angle that I have is 30 degrees. And the next one I'll have is 60 degrees, followed by the fact that 120 degrees has a related acute angle of 60 degrees. 150 degrees has a related acute angle of 30 degrees. The angle between 180 degrees and 225 degrees is 210 degrees because this angle has a related acute angle of 30 degrees. If I have an angle here, that means this angle of 240 degrees has a related acute angle of 60 degrees. This angle here, which is 300 degrees, has a related acute angle of 60 degrees, followed by this last angle, 300 degrees, which has a related acute angle of 30 degrees. So let me write all of that down. So I have 30 degrees, 60 degrees, 120 degrees, 150 degrees, 210 degrees, 240 degrees, 300 degrees, and 330 degrees. So there's quite a lot of corresponding angles when you have a related acute angle of 30 degrees or 60 degrees. So for all of these lines that I've drawn, you are able to come up with the exact value of the trigonometric ratio. So for question 3, it says almost every time trig functions are used, there is rounding error. However, it is possible to find exact values for some special angles. Draw 2 special triangles and explain where the side lengths come from. So there are 2 right angle triangles, and I'm going to start off with the first one. And think about it this way. Think about drawing a right angle isosceles triangle. And let's say you had to just wing it and you just had to draw it, right? So we want to make it as simple as possible, and that's what we're going to do. So when I'm drawing my right angle triangle, the simplest way to draw it is that I'm going to make this side length 1 and this side length 1. Okay? Seems simple enough. So if this is a right isosceles triangle, which means two sides are equal, like so, that means that these two angles will also be equal. So a triangle adds up to 180 degrees. So 180 degrees minus 90 degrees is 90. That means these two angles will need to share 45 degrees each. At this point, I need to figure out what my hypotenuse is. And so a squared plus b squared equals c squared is equal to 1 squared plus 1 squared, which is c squared. 1 plus 1 is c squared, so 2 is equal to c squared, and therefore c is going to equal to square root of 2 in just the positive version because we're dealing with dimensions and we only grab the positive version when we're dealing with dimensions. Based on this is my right angle isosceles triangle where my side lengths are 1, 1, and square root of 2. So there is a reason why I drew this right angle triangle in green. It's to show you that I am indicating that all of these angles I can find using this right isosceles triangle with 45 degrees. So that is our first special triangle, and I hope you realize that you're basically starting off with the simplest right angle triangle with 45 degrees, 90 degrees. So for this 45 degrees, it has a corresponding side of 1. This 45 degrees also has a corresponding side of 1 because it's an isosceles triangle, meaning two equal sides. The 90 degrees angle has a corresponding side of square root 2.
Okay, so for the other equilateral triangle, what I'm going to start by doing is drawing the equilateral triangle. So it's like the next simplest triangle that we could come up with. So this is how I'm going to start drawing my equilateral triangle. So think about what is another kind of triangle that is simple to draw. And so what I mean is I'm going to start by drawing an equilateral triangle, but I'm going to cut it in half at the end. And therefore, that's the reason I'm going to write 2's all the way around for all the equal sides. So with this triangle, I'm actually going to cut it in half. And we're primarily looking at just one side of this triangle because they're parallel, so it's the exact same thing. And so based on this diagram, we can tell that the hypotenuse is a 2, right? Meanwhile, because I cut this in half, that means this is a 1 exactly, right? And let's think about our angles. Originally in this equilateral triangle, since all angles in a triangle add up to 180, because it was originally an equilateral triangle, I need to divide all the 180 degrees by 3. So it is 60 degrees for each angle originally. And because this is 60 degrees and this is 90 degrees, what does that make this? Well, it's exactly half of 60, and therefore that is 30 degrees. So this one side of the right angle triangle is how we draw it. And as I get more comfortable with this, you would just draw that equilateral triangle. But as you're drawing it, you're kind of imagining that you have started off with the initial equilateral triangle. This blue triangle, keep in mind that this triangle helps us with all the blue angles that I have indicated above. So I'm not quite done yet because as you notice, I have a 2 and a 1 for some of its sides, but I have no idea what this side is equal to. And at that point, I'm going to do Pythagorean theorem. And so my A value is going to be, let's say, a 1 because that's the other side, but I don't know what my B is, but I do know my hypotenuse, which is 2. So I get 1 plus b squared is equal to 4. I'm going to subtract 1 on both sides. Therefore, b squared is equal to 3. Gonna square root both sides. Because we're dealing with sides, I'm only going to grab the positive version, like so. And so b is equal to plus square root of 3. This new information, I can say this is square root 3. The first one, which deals with the angles of 45 degrees and 90 degrees and the sides of 1, 1, and square root 2. Meanwhile, the other right angle triangle, which comes from an equilateral triangle with side length 2, gets cut in half, so then you have side lengths 2, 1, and
square root of 3.
and where 2 is the hypotenuse. Use when dealing with ratios. Draw different size triangles and label the dimensions, show that ratios are still the same. So think about like a cookie recipe or a baking recipe. Will the ratio of how you're cooking change? If you're cooking for 12 people versus for 2 people, will the ratio of how you're using the recipe change? Think about that for a second. Well, it shouldn't, because you're just changing how many times you're going to have that ingredient. And so for this example, if you have a right angle triangle with 90 degrees with 45 degrees, and these are the dimensions and angles that are given. If you went ahead and try to find the sine of 45 and sine of 45 for the one above versus the one on the bottom, and we do that for a sec, well, they're both equal to opposite over hypotenuse. And when I plug this in, well, my opposite, well, it doesn't really matter which angle you're looking at because they're the same thing. So if I'm looking at it from this angle, my opposite is 1, and my hypotenuse is square root 2. So we have 1 over square root 2, and that is for the above triangle. When I look at the bottom triangle, again, if I'm looking at this 45 degrees, it doesn't really matter which one. This 45 degrees, if you're looking at the opposite, that's a 5, and the hypotenuse is 5 square root 2. 5 divided by 5 square root 2. Notice that it reduces because the 5's cancel out, and you get 1 over square root 2 again. And this time, this was regarding the triangle on left. Okay, as you notice, the ratios of the two are the same. And that's why these triangles are so special, because as long as we're dealing with a triangle that has these angles, we're dealing with ratio, and so our answers for these ratios will simplify to the same thing. This time, if I have a different version of the blue triangle with dimensions of 90 degrees, 60 degrees, 30 degrees with a hypotenuse of 6, 3, and 3 square root 3 as a side. I have cos 60 degrees, which is adjacent over hypotenuse, and cos 60 again for adjacent over hypotenuse. For the above triangle, we notice that we have an adjacent of 1 and a hypotenuse of 2. And so we get 1 over 2. You looked at the triangle on the bottom, and you have 60 degrees, so I have to look at my 60 degrees as my reference angle. Adjacent, the side that is next to that is 3, and my hypotenuse is 6, so that's 3 over 6, which reduces to 1/2. You basically notice in both cases that you're getting 1/2 every time. And so
The reason being is you're dealing with similar triangles. There are two triangles where one is a bigger or smaller version of another, but the angles are consistent. And so the ratios are going to be equivalent due to that. So let's take a look at these the next question. Question 5. Find the exact values for all the dimensions of the following diagram. Okay, so we have a triangle over here. It's an isosceles right angle triangle, and because this is a right angle, that makes this a right angle, and the rest. So let me focus on one part at a time. So on this first triangle, these angles must be 45 degrees if this angle is 90, and because this side and this side are equivalent, and so as a result this side was going to be 12. I don't know yet what this side is, and I just gave it a variable. Any kind of variable from A to Z is fine. So what I did as my step 1 is that I try to consider the angles above, and the angles above in that case must be 45. Next, for step 2, well, how do you think I can find that missing dimension? I was able to find that 12 right away, but I can find Z by doing, Well, referring to my right angle triangle, which is over there, these are the two that I'm referring to. While I'm dealing with this first triangle, because I noticed the 45, it's tilted and you have to be able to look at it in different angles. But if this is, instead of having ones, I have 12, that means I need to do 12 times square root 2 because all of these side lengths have been multiplied by 12. So for my z, I have 12 times square root 2. The square root 2 is the original hypotenuse, so my z is equal to 12 square root 2 units. Now let's take a look at the right angle triangle on the side. And so this is a 90 degrees because the other one is a 90 degrees. This one's 30 degrees. Well, 90 plus 30 is 120. So 180 minus 120 makes this 60 degrees. So step 1, the other angle must be 60 degrees, and I did that by doing 180 minus the sum of 90 plus 30 in brackets, and so theta is equal to 60 degrees. Step 2. I have a side length of 12 right here, right? And so I'm going to take a look at the triangle on the side. And sometimes I want to rewrite it so that I can imagine it more. Because right now the 60s here, the 30s here, and maybe it's not as clear for you. So I'm going to rewrite that triangle so that it's tilted. So this is my tilted version. I have a hypotenuse of 2. That's how I can start off. I cut it in half so I have it as 1. Actually, not over there. I cut it in half so that 1 is here because this is where my 60 degrees is. And it's like I am saying that it was originally like this triangle. And I cut it in half, and that's why this is 1. And that makes the other length square root 3 based on our calculation over there. And so when I look at this tilted model, I can better compare the two. Since b is equal to 12, instead of what value? Instead of 1. Then a must be equal to what? Well, basically my 1 became a 12, and so my square root 3 is going to become 12 times square root 3 instead of square root 3. For my step 3, instead of 2, I should have 2 times 12. So I'm going to write 2 times 12 for my hypotenuse. And so C equals 24 instead of 2 because I times that by 12. So you basically times 12 from the special triangle to this triangle, and you also times 12 from this triangle to this triangle. Okay, and I circled the fact that we are changing it by a factor of 12.
Okay, so on to the next page, I'm going to write down some of the instructions on how to approach some of these questions. First step is that you're going to draw the angle. You're going to draw the angle that they present to you, or working with the principal angle that is in standard position, meaning being in between 0 degrees to 360 degrees. You're going to draw the triangle towards the x-axis, meaning I'm going to draw my triangle so that I can create some kind of related acute angle with it and not towards the y-axis. So you're going to label it. A lot of these angles are going to deal with special angle triangles. And so you're going to label it so that if you're dealing with the 30-60 degrees right angle triangle, that the corresponding angle to square root 3 is 60, corresponding side to 2 is 90 degrees, 30 degrees has a corresponding side of 1. And then the other triangle, the 45, 45, 90 degree angle, again, has its corresponding angle and side, and it's been kind of color coded. Next, you're going to insert any negatives where applicable. So for example, for x or y, you might have some negative values, whereas radius is always going to be positive because that's like it's a dimensional figure. And lastly, you're going to use any relative definitions. So on to the first question, we have number 6, find the exact values of each of the following without using the calculator. So the reason they're saying that is that for some of these questions that you might have radicals involved, and therefore if you use a calculator, it will be obvious because you're gonna get a decimal value rather than an exact radical version. So for cosecant of 330 degrees, that's another way of representing that is as a reciprocal of sine of 330 degrees. So I remember that sine is y over radius, therefore the reciprocal of that is radius over y. So at this point, I'm not sure what to sub in, and so I'm going to draw my x and y axis, and with my angle of 330 degrees, it's going to go right there. Here to here is my principal angle of 330 degrees with the related acute angle of 30 degrees. So I have done step 1, and I'm going to do step 2, which is draw the triangle towards the x-axis. So I'm going to compare these two triangles because I noticed a 30 degrees there. This is 30 degrees, this is 90 degrees, and therefore this has to be 60 degrees. I'm going to start filling it in based on the triangle. And so 30 degrees has a corresponding side of 1. 60 degrees has a corresponding side of square root 3. 90 degrees has a corresponding side of 2. And that is by looking at this triangle right here and comparing the two. Okay. So now I'm going to start filling it in. So with this 1, 2, and 3, let me interpret that for a second. Well, this should actually be a negative because we are dealing with a negative y value. And so that's why it's helpful to write y here, radius here, and x here. Once this is labeled, it becomes easier to plug in. So radius over y. So radius is equal to 2, and y is equal to negative 1. And therefore, my answer to cosecant 330 degrees is negative 2 exactly. And so for this particular one, if you did 1 divided by sine 330 right on the calculator, you would have gotten this exact version. But we're practicing how to do it by hand, so you know how to do it when it is not exact and it cannot be calculated using a calculator.
So for cos 720 degrees, again, you want to be dealing with things in standard position if possible. And if I subtract that by 360, I get cos 360 degrees. And they're going to result in the exact same value because they're coterminal angles. And so I'm going to work with that part. Cos 360, another version of that is cos 0 degrees because they're at the exact same spot. They're all coterminal angles. And I again get that by subtracting by 360. So by definition, cos has a definition of x divided by radius. So at this point, I'm going to draw my x and y axis and draw my coordinate. My coordinate is going to lay right here. If I'm looking at it as a unit circle and values of 1, 0, because it's going to be easiest to approach it with a unit circle. It doesn't matter what radius I go through it as, it's going to result in the same trig ratio. And so I have a coordinate of 1 and 0, so x and y, and I'm going to plug in from there. So x is equal to 1, my y I don't need, my radius is 1, and so my cos 720 is equal to 1. Question C. So by definition, sine theta has a definition of y over r according to my circle and according to how I draw my right angle triangle. So when I draw my x and y axis, my principal angle is, my terminal arm is going to end up right there. And so this is 315 degrees. I'm going to start drawing my acute triangle. And so this has to have a related acute angle of 45 degrees because I'm doing 360 minus 315 in my head. And so if that's the case, this is 90 because I've drawn myself a right angle triangle, and this is 45 degrees. And you're looking at this triangle over here and this triangle over here and trying to compare the two. Well, a 45-degree angle has a corresponding side of 1 and 1, but its hypotenuse is square root 2. If we take a moment, we have to insert any negatives, meaning I need to actually put a negative in front of that because that's where my y's are negative. And so again, I'm going to put y there and x there because this is my x and this is my y and this is my radius. I'm going to plug it in. So my y has a value of -1. My radius has a value of square root 2. Am I done at this point? I still need to rationalize, so I'm going to multiply that by square root 2, the numerator by square root 2, and I'm going to get negative square root 2 divided by 2. And that is my final answer for sine 315 degrees in exact form.